आज चाहिँ च्याप्टर 6 using a neural network to feed the data. This chapter covers nonlinear activation function as the key difference compared with linear model. Working with PyTorch and N module, solving a linear fit problem with a neural network. So far, we have taken a close look at how a linear model can learn and how to make that happen in PyTorch. We have focused on a very simple regression problem that used a linear model with only one input and one output. Such a simple example allowed us to dissect the mechanism of a model that learns without getting overly distracted by the implementation of the model itself. As we saw in the overview diagram in chapter 5, figure 5.2 repeated here as figure 6.1. The exact details of the model are not needed to understand the high level process that trains the model. Back propagating errors to parameters, then updating those parameters by taking the gradient with respect to the loss is the same no matter what the underlying model is. Okay, the learning process inputs the desired output ground truth भयो forward pass गर्यो actual output given current weights. So error loss गर्यो error loss बाट change weights to decrease the error फेरि backward हुँदा iterate हुन्छ. Okay, in this chapter we will make some changes to our model architecture. We are going to implement the full artificial neural network to solve our temperature conversion problem. We will continue using our training loop from the last chapter along with our Fahrenheit to Celsius sample split into the training and validation sets. We could start to use a quadratic model, rewriting model as a quadratic function of the inputs. For example, y is equal to a, okay, a into x square plus bx plus c. Since some models will be differentiable, PyTorch will take care of the computing gradient and the training loop. Okay, computing gradient the auto grad ले handle गरिहाल्छ, not big deal होइन. And the training loop would work as usual. That wouldn't be too interesting for us though, because we will still be fixing the shape of the function. This is the chapter where we begin to hook together the foundational work we have put into the PyTorch features you have been using day in and day out as a work on your project. You will gain an understanding of what's going on underneath the porcelain of the PyTorch API rather than it just being so much black magic. Before we get into the implementation of our new model, let's cover what mean by neural network, artificial neural network, artificial neuron. At the core of the deep learning are the neural networks, mathematical entities capable of representing complicated functions through a composition of simpler function. The term neural network is obviously suggestive of a link to the way our brain works. As a matter of fact, although the initial models were inspired by neuroscience, modern artificial neural network bear only a slight resemblance to the mechanism of neurons in the brain. It seems likely that both artificial and the physiological neural networks use vaguely similar mathematical strategies for approximating complicated functions, because that family of strategy works very effectively. Note, we are going to drop the artificial and refer to the construct as just neural networks from here forward. Okay, the building block of this complicated function is a neuron, as illustrated in the figure 6.2. At its core, it is nothing but a linear transformation of the input. For example, multiplying the input by a number, the weight, and adding the constant, the bias, followed by the application of a fixed nonlinear function referred as the activation function. Similarly, mathematically, we can write this as okay, O is equal to f power w into x plus b, with x as the input, w is the weight or the scaling factor, and b as the bias or offset. F is our activation function set to the hyperbolic tangent and the tan h function here. In general, x and hence O can be simple scalar or vector value, meaning holding many scalar value. And similarly, okay, the neuron. Okay, 10, okay, 10h ma. So 10h ma किन दिइरहेको छ भने segment function type गराउनु खोजेँ. Non-linear function activation, okay. So 10h मा चाहिँ kind of sigmoid तर -1 देखि 1 आउने हो. Okay. मैले न्युरल नेटवर्कको त्यसो भए ऊ चाहिँ युज गरिहेर्नु. Okay. This mouse calculator. 10h in mouse. Well, कति complicated हो. तर okay, यो त हैन. How to implement 10h? Saturator. What 10h मा त लेख्दै चल्दो रहेछ त. Okay. F of x is equal to 10h. 10h लेख्दै भन्छ TANH x. Okay. -1. Okay, -1 बाट 1 आउँदो रहेछ. So sigmoid function ले त 1/1 plus 1 plus eco power minus z x. Okay, योबाट चाहिँ 0 बाट 0 र 1 आउँछ. त्यही भएर sigmoid function युज गर्ने हो. के गर्नलाई चाहिँ केमा बिजी भयो फेरि. Okay, can be single scalar or matrix, while B is a scalar or vector. The dimensionality of the input and the width must match, however. In the latter case, the previous exception is referred as a layer of neurons, since it represents many neurons via the multidimensional weight and biases. Okay, composing a multi-layer network. A multi-layer neural network, as represented in figure 6.3, is made up of a composition of functions like those we discussed above. X1 is equal to okay, x1, x2, y. Okay, here the output of the layer of neuron is used as an input for the following layer. Remember that W0 where is a matrix and X is a vector. Using a vector allows W0 to hold an entire layer of neuron, not just a single weight. Okay. So 0 is equal to 10, Wn, yeah, okay. So X is equal to ln activation. Understanding the error function, okay. An important difference between our earlier linear model and what we will actually be using for deep learning is the shape of the error function. Our linear model and this error least squared loss function had a convex error curve with a singular clearly defined minimum. Okay. If we were to use other methods, we could solve for the parameter minimizing the error function automatically and definitively. That means that our parameter updates were attempting to estimate the singular correct answer uh, they as best they could. Neural networks do not have the same property of a convex error surface even when using the same error square for loss function. There is no single right answer for its parameters. We are attempting to approximate. Instead, we are trying to get all of the parameters when acting in concert to produce a useful output. Since that useful output is only going to approximate the truth, there will be some level of imperfection where and how imperfectious manifest is somehow arbitrary, and by implication the parameters that control the output and hence the imperfections are somehow arbitrary as well. This result in neural network training looking very much like parameter estimation from a mechanical perspective, but we must remember that the theoretical underpinning of are quite different. A big part of the reason neural networks have convex error surface is due to the activation functions. Okay, the ability of the examples of the neurons to approximate a variety the very very wide range of useful function depends on the combination of the linear and the non-linear behavior inherent to each neuron. All we need is activation. Okay, as we have seen, the simplest unit in deep neural network is a linear operation, scaling plus offset followed by a activation function. We already had our linear operations in our latest model. The linear operation was the entire model. The activation function plays two important roles in the linear part of the model. In the inner part of the model, it allows the output function to have different slopes at different values. Sometimes a linear function by definition cannot do. By trickyly composing these different slope parts for many outputs, neural networks can approximate arbitrary function as well as we see in section 1.6.3. Uh, at the at the last layer of the network, it has the role of connecting the outputs of the preceding layer operating into a given range. Let's talk about what's the second point means. Pretend that we are assigning a good doggo score to images. Picture of retrievers and spaniel would have a higher score, while image of the airplanes and the garbage truck should have a low score. Okay, bear picture should have a lowest score too, although higher than garbage trucks. The problem is we have a function, we have to define a high score. We have got the entire range of floater to work with, and that means we can go pretty high even if we say it's a 10-point scale. There is still the issue that sometimes our model is going to produce a square of 11 out of 10. Remember that on the root it's sum of x into w into x plus b in matrix multiplication, and those won't naturally limit themselves to a specific range of outputs. Okay, for an integrated approximation of this universal approximation to a property, you can pick a function from figure 6.5 and then build a building block function that is almost zero is in most part of the positive around x is equal to 0 from scaled including multiplied by negative numbers and translated copies of the activation function. With scale translated and dilated squeeze along the axis copies of this building block function, you can then approximate any continuous function. In figure 6.6, the function in the middle row of the right middle row to the right could be such a building block. Michael Nielsen has an interactive demonstration in this outline work. Okay, neural networks and deep learning it. Okay, capping the output range. We want to formally constrain the output of our linear operation to a specific range so that the consumer of this output doesn't have to handle numerical inputs of puppies at 12 by 10, beer at minus 10, and garbage truck at minus 1000. One possibility is just cap the output values. Anything below 0 is set to 0 and anything above 10 is set to 10. That's a simple activation function called torch.nn.hard 10h. Okay, hard 10h. Okay, hard 10h. PyTorch go. PyTorch. PyTorch go. PyTorch go nn dot 10h. Then hard 10h something. Hard 10h. Hmm. Minimum value minus 1.0 beta, max value 1.0 in place false. Okay. Okay. Minimum minus 1 down, maximum value 1 down, and zero is okay. Hmm. compressing the output range. Another family of functions that work well is torch.nn.segment, which includes 1 upon 1 plus eco power minus z x rahe. Okay. Torch 10h and others that we will see in a moment. These functions have a curve that asymptotically approaches 0 or minus 1 as x goes to negative infinity, approaches 1 as x increases, and have a mostly constant slope at x is equal to 0. Consequently, function shape this way works well because there is an area in the middle of our linear function output that our neuron, which again is just a linear function followed by an activation, will be sensitive to. While everything get lumped next to the boundary values, as we can see in figure 6.4, our garbage truck gets a square of minus 0.97, while bears and foxes and wolves end up somewhere in the range of minus 0.3 to 0.3 range. Okay, undersaturated, sensitive, oversaturated. Not dog, very much dog. Okay. This results in the garbage truck being flagged as not dog, our good dog mapping to clearly a dog, and our beer ending up something in the middle. In code, we can see the exact values. Garbage truck, okay. With the beer in the sensitive range, small changes to the beer will result in the noticeable change to the result. For example, we could switch from a grizzly to the polar bear, which have vaguely more traditionally canine face, and see a jump up the y-axis as we slide towards a very much a dog in the graph. Conversely, a koala bear will register as less dog-like, and we will see a drop in the activated output, and there isn't so much we could do to the Darvish truck to make it register as dog like, though even with the drastic changes we might only see a shift from minus 0.6 0.97 to minus 0.8 or so. More activation functions. There are quite a few activation functions, some of which are shown in the figure 6.5. The first column, the first column we see and the smooth function 10h and soft plus, while the second column has a hard version of the activation function to their left, hard 10h, and the ReLU for rectified linear output लिखी रेलु पनि हुन्छ कि होइन deserves special note as it is currently considered. Okay, 10h smooth हुन्छ अरे, hard 10h र रेलु अलि hard छ अरे, अनि okay sigmoid sigmoidちょっと違うかなあとसेम सेम 0 र 1 को बिचमा जाने लिख रेलु ओके सो रेलु चाहिँ एक्ज्याक्टली भन्दा चाहिँ रिक्युलेट अलिकति लिक गर्दो रहेछ ओके one of the best performing general activation functions. Many state-of-the-art results have used it. The segment activation function, also known as a logistic function, was widely used in early and deep learning network, but has since fallen out of common use, except where we explicitly wants to move to the 0-1 range. For example, when the output should be probability. Finally, the leaky ReLU function modifies the standard ReLU to have a small positive slopes rather than being strictly 0 for negative inputs. Uh, Typically, this slope is 0.01, but it is shown here with the slope 0.1 for clarity. Choosing the best activation function. How to choose a best activation function? The activation function are curious because with such a wide variety of proven successful ones, many more than shown in figure 6.5, it's clear that there are few, if any, strict requirements. As much we are going to discuss more generalities about activation functions that can probably be trivial disproved in the specific. That said, by the definition, activation function are no are non-linear repeated application of w into x plus wx plus p without an activation function result in a function of the same affine linear form. The non-linearity allows the overall networks to approximate more complex functions. differentiable, so the gradient can be computed through them. Points discontinuous, as we can see in hardness or relief are fine. Without these characteristics, the network either falls back to being a linear model or becomes difficult to train. The following are the true for the functions. They have at least one sensitive range where non-trivial changes to the input results in the corresponding non-trivial change to the output. So they have at least no one sensitive range where non-trivial changes to the input results in the corresponding non-trivial changes to the output. Okay, this is needed for training. Many of them have an insensitive or saturated range where change to the inputs result in little or no change to the output. Okay. By the way of example, the hardness function could easily be used to make a piecewise linear approximation of a function by combining the sensitive range with different weights and bias on the input, often but far from universally so. The activation function we will have at least one of these: a lower bound that is approached or met as the input goes to negative infinity, or similar but inverse upper bound for positive infinity. Thinking of what we know about how backpropagation works, we can figure out the error will propagate backward through the activation more effectively when the inputs are in the response range, while errors will not greatly affect neurons for which the input is saturated, since the gradient will be close to zero due to the flat area around the output. Okay, but sorry, put together all the results in the pretty powerful mechanism. We are saying that in a network built out of linear plus activation units, when different inputs are presented to the network A, different units will okay different unit will respond in a different range for the same inputs. And B, the error associated with those inputs will primarily affect the neurons operating with the sensitive range, leaving other units more or less unaffected by the learning process. In addition, thanks to the fact that derivatives of the activations with respect to its inputs are often close to 1 in the sensitive range, estimating the parameters of the linear transformation through gradient descent for the unit that operates in that range will look like a lot like the linear fit we have seen previously. What are we are starting to get deeper in intuitions for how joining many linear plus activation units in parallel and stacking them one after another leads us to a mathematical object that is capable of approximating complicated functions. Different combination of units will respond to inputs in different ranges, and those parameters for those units are relatively easy to optimize through gradient descent, since learning will behave a lot like that of a linear function until output saturates. What learning means for a neural networks: building model out of a stack of the linear transformation followed by differentiable action activations leads to models that can approximate highly nonlinear process, and those parameters can we can estimate surprisingly well through gradient descent. This remains the true even when dealing with models with millions of parameters. What makes using deep neural networks so attractive is that it saves us worrying too much about the exact function that represents our data, whether it is quadratic, piecewise, polynomial, or something else. With a deep neural network, we have a universal approximator and the method to estimate its parameters. This approximator can be customized to our needs in terms of model capacity and its ability to model complicated input output relationship just by composing simple building blocks. We can see some examples of this in figure 6.6. The upper four left graph shows our neuron ABCD with each with the own weight and mass. Okay, 6.6. Okay. Good. Teenage A plus B, C plus D, teenage, okay. Uh, each neuron uses so the four left graph shows us in ABCD and is with its arbitrarily chosen weight and math. Each neuron uses the 10 activation functions with the minimum of -1 to max of 1. The verified no weights and the biases move the center of the center point and changes how drastically the transformation from min to max happens, but they clearly all have the same general shape. The columns to the right of those show points, show pairs of neurons added together, A plus B and then C plus D. Here we start to see some interesting properties that mimic a single layer of neuron. A plus B shows a slight S curve with the extremes approaching zero, but both a positive bump and a negative bump in the middle. Conversely, C plus D has only a large positive bump which is peaks at a higher value than our single neuron max of 1. In the third row, we begin to compose our neurons as they will be in a two-layer network. Both C A plus B and D A plus B have the same positive and negative bumps that A plus B shows, but the positive peak is more subtle. The composition of C A plus B A plus D A plus B shows a new property to clearly negative bumps and the possibly a very subtle second positive peak as well as to left of the main area of interest. Hmm. Again, these neurons parameters were chosen only to have a visually interesting results. The training consists of finding acceptable value for these weights and bias so that the resulting networks correctly carries out a task such as predicting likely temperature given geographic coordinates and time of the year. By carrying out the task successfully, we mean obtaining a corrected output on unseen data produced by the same data generating process used for training data. A successfully trained network through the values of its weights and bias will capture the inherent structure of the data in the form of meaningful numerical representations that work correctly for previously unseen data. Okay, let's take another step in the realization of the mechanics of learning. Deep neural networks give us the ability to approximate highly nonlinear phenomena without having an explicit model for them. Instead, starting from a generic untrained model, we visualize it on the task by providing a subset of inputs and outputs and loss function from which is to back propagate. Specializing a generic model to a task using examples is what we refer to a learning. Because the model wasn't built with a specific task in the mind or no rules describe how the tax or would included in the model. For our thermometer example, we assume that both thermometers measure temperature linearly. That assumption is where we implicitly encoded a rule for our task. We hard-coded the shape of our input-output function. We couldn't have approximated anything older than data points sitting around online. As the dimensionality of a problem grows, and that is many inputs to many outputs, the many inputs outputs relationship get complicated. Assuming a shape of a input output function is unlikely to work. The job of a psychiatrist or an applied mathematician is often to come up with a functional description of a phenomenon from first principle so that we can estimate the unknown parameters from measurements and get an accurate model of the world. Deep neural networks, on the other hand, are families of functions that have the ability to approximate a wide range of input-output relationship without necessarily requiring up to come up with an explanatory model of the phenomena. In a way, we're renouncing an explanation in exchange for possibility of tackling increasingly complicated problems. In other way, we sometimes lack the ability, uh, information, or computational research to build an explicit model of what we are presented with. So data-driven methods are only way forward. So PyTorch channel model, by this talking about PyTorch neural network is probably making you really curious about building one from the scratch with PyTorch. मैले बनाइसकेको छु ट्युटोरियल भिडियोमा. Our first step will be replace our linear model with a neural network unit. This will be somehow unless step backward from the correct perspective, since we have already verified that our calibration only require a linear function, but we still be instrumental for starting a sufficiently simple program and scaling up later. uh, PyTorch has a whole submodule dedicated to neural networks called torch.nn. It contains the building block needed to create all types of neural network architecture. These building blocks are called modules. Okay. In PyTorch parlance, such building blocks are often required to the layers in other frameworks. Okay. A PyTorch module is a Python class deriving from an another module based class. A module can have one or more parameters instance as attributes, which are tensors whose values are optimized during a training process. Think W and V in our linear model. The module can also have one or more submodules, subclass of another module as attributes, and it will be able to track their parameters as well. Note the submodules. Sorry. The submodule must be top level attributes, not buried inside list or dictionary instances. Otherwise, the optimizer will not be able to look at the submodules and hence their parameters. Since for situations where our model requires a list of dictionary of submodules, PyTorch provides another module list, the and another model linked. So unsurprisingly, we can find the subclass of another module dot another linear, which applies an affine transformation to our input via the parameter attributes weights and bias, and it's equivalent to what we implemented earlier in the thermometer experiment. We'll now start precisely where we left off and convert our previous code into a form that use an using call rather than forward. All PyTorch provided subclass of an ended module have their call method defined. This allows to instantiate an ended linear and call its is at as if it was a function like or so. Okay. Import torch.nn as nn. Linear model is an ended linear 1 linear model t is on val. आइनो थियो भएर यसलाई म ट्राई गर्छु हेर्दैन. Calling a instance of an ended module is set of arguments end up calling a method named forward with the same arguments. The forward method is what executes the forward computation, while call does not does other rather than important chores, because the after calling forward, so it is technically possible to call forward directly and it will produce the same output as call, but this should not be done with user code. Here the implementation of module call. We left our bits related to the JIT and and made some simplification for clarity. Torch.nn.modules module.py. Okay, call okay for hook in self.forward pre-hooks dot values. Hook is equal to height. Hook is equal to hook is equal to self input. Result is equal to self dot forward. Okay. So you हेर्दाखेरि for hook in self भने यो पनि भयो हैन. We can see that there is a lots of hook that won't get called properly if we just use forward directly. Returning to the linear model, back to our linear model, the constructor to nn dot linear accepts the three arguments: the number of input features, the number of output features, and the and last one is what required bias or bias like true false गर्ने हो. Require grad, which one? Okay, and whether the linear function includes a bias or not हो सँग त लागिरहेको थियो क्या लिनियरमा गएर पास गरेको थियो एउटा नम्बर अफ इनपुट फिचर्स अनि आउट फिचर्स अनि एउटा बायसलाई ट्रु गर्यो अनि चाहिँ ग्राड रिक्वायर्ड ग्राडलाई ट्रु गर्छ नभए फल्स गर्छ. ओके, the number of features the number of features in our case just refers to the size of the input and the output tensor for the module, so 1 and 1. If we use both temperature and barometric pressure as input, for instance, we could use two features in input and one features in our output. As we will see, for more complex model with several intermediate modules, the number of features will be associated with the capacity of the module. We have an instance of another linear with one input and one output features that only requires one weight and bias. So linear model dot weight parameter contains okay, required grad true there is a bias. Okay, and then that linear model is required grad like true is okay, linear model dot bias. We can call the module with some input x is equal to torch dot ones. Okay, टेन्सर बनाएर के गरेको त एक्स्ट्रा अनि लिनियर मोडलमा पास गरिदियो. Although PyTorch let us get away with it, we don't actually provide an input with the right dimensionality. We have a model that looks one input and produce one output, but PyTorch nn.model and its subclasses are designed to do so on multiple samples at the same time. To accommodate multiple samples, modules expect the zero dimensions of the input to be the number of samples in the batch. Okay, we encountered this concept in chapter 4 when we learned how to arrange real world data into tensor. Okay, batching inputs. Any module in NN is written to produce outputs for the batch of multiple inputs at the same time. Thus, assuming we need to run nn.linear on 10 samples, we can create a input tensor of size b into a very say यसको input size को जान्छ होला n okay, where b is the size of the batch and n is the number of input features. Okay, and run it once through the module, for example. So x is equal to torch dot once 10 10वटा भनेपछि रो 10वटा कोलम एउटा अनि ब्राकेट दुईटा हुन्छ, अगाडि एउटा स्क्वायर ब्राकेट भित्रपट्टिको चाहिँ क्लोजिङ गरेर त्यो 10वटा हुन्छ. यो दिस इज अ टु डाइमेन्सनल 0 and 1 dimensional 2 dimensional data. Let's dig into what's going on here with figure 6.7. where is 6.7? Okay, 3 RGB pictures together and feed into the neural network. The output is a batch of 3 vectors of size 4. Let's dig into the what's going on here in the figure 6.7, showing a similar situation with batch image data. Our input is पहिला के हुन्छ भन्दा ब्याच साइज बी इन्टु सी भनेको च्यानल हुन्छ, त्यसपछि हाइट अनि विथ इज ब्याच साइज अफ 3 सेज डग एग बर्ड एन्ड देन कार 3 च्यानल रेड ग्रीन ब्लू. ओके, मेक सेन्स. And the unspecified number of pixels for width and height. Okay, as we can see that the output in the tensor of size b into n out, where n out is the number of output features, b is the best size by yellow. So this is the तीनटा दिइरहेको छ रेड ब्लू मान्छे तीनटा कलर च्यानल भयो, तीनटा दिस इज द ब्याच बी इन्टु अनि तीनटा भनेको चाहिँ के रेड ब्लू ग्रीन आरजिबी भइहाल्यो अनि हाइट इन्टु वेट यो चाहिँ डाइमेन्सन उसको साइज हुने भयो इनपुटको साइज. ओके, The reason we want to do this batching is multifaceted. One big motivation is to make sure the computation we are asking for is big enough to saturate the computing resources we are using to perform the computation. GPU in particular are highly parallelized, so so a single so a single input on a small model will leave most of the computing units idle. Okay, by providing batches of inputs, the calculation can be spread across the otherwise idle units, which means the batch results come back just as quickly as single results would. Another benefit is that some advanced models use statistical information from in the entire batch, and those statistics get better when larger batch sizes. Back to our thermometer data, TU and TC were two ID1D tensor of size B. Thanks to broadcasting, we could write our linear model as W into X plus V, where W and B were two scalar parameters. This worked because we had a simple input features. If we had to, we will need an extra dimension to turn that 1D tensor into a matrix with samples in the rows and the features in the columns. That's actually what we need to do to switch to using nn.linear. We reshape our b inputs to b into nin, where nin is the one. So number of input is one, number of input features is equal to one. Okay, this is easily done with unsqueeze. So what will do unsqueeze ले एउटा डाइमेन्सन थपिदिन्छ. So if toss.insert is unsqueeze 1 गरेको adds one extra dimension to axis 1 okay. Oh, we are done. Let's update our training code. First we replace our handmade model with nn linear 1 comma 1, and then we need to pass the linear model parameters to the optimizer. Linear model is equal to n linear 1 1, optimizer is equal to optim.sgd, linear model dot parameters भयो. ओके भनेपछि हामीले यहाँ लिनियर मोडल इज इक्वल टु n.n भयो ल अप्टिमाइजरमा nn. ओके टर्च डट अप्टिमको एसजिडी हो कि स्टोकेस्टिक ग्रेडियन्ट डिसेन्ट लिनियर मोडलमा प्याराम्स इज इक्वल टु लिनियर मोडल डट प्यारामिटर्सहरू पास गरेर अनि लर्निङ रेट इज इक्वल टु 1 इको पावर -2 दिएको भइहाल्यो. Earlier, it was our responsibility to create parameters and pass them as the first arguments to optim.std gradient descent algorithm. Now we can use the parameters method to ask the nn.module for the list of parameters owned by it and any of its submodules. यसलाई त एक्स्ट्रा गर्न सकिन्छ यदि मोडलको स्टेट डिक्सनरीबाट नै हेर्न सकिन्छ. लिनियर डट मोडलको प्यारामिटर्स गरेर दुईटा देखाइरहेको छ, लिस्ट गरेर चाहिँ लिनियर प्यारामिटर्स गरेर गर्न सकिँदैछ. But the state parameter state dictionary at the well. This call recurses into submodules defines in the modules init constructor and returns a flat list of all parameters encountered, so that we can conveniently pass it to the optimizer constructor as we did previously. We can already figure out what happens in the training loop. The optimizer is provided with a list of tensors that we defined with required grad true. So required grad true गर्यो भने चाहिँ अटोग्राडले के गर्छ, ट्र्याकिङ गर्न सुरु गर्छ प्यारामिटर्सलाई. All parameters are defined this way by definition. Since they need to be optimized by gradient descent, when training lossलाई चाहिँ backward ल्याइदाखेरि अटोग्राडले चाहिँ हाल्छ हैन. Okay, is called grad is accumulated on the leaf node of the graph, which are precisely the parameters we pass to the optimizer. At this point, the SGD optimizer has everything it needs. When optimizer.step is called, it will iterate through its parameters and change it by an amount proportional to what is stored in the grad attributes. Pretty clean design. Let's take a look at a training loop now. And definition training loop is equal to optimizer model function to okay सबै दिएर रहेछ for epoch in range 1. सो लाई मोडलमा अगाडि गरेर चाहिँ फरवर्ड पास गर्यो, ट्रेनलाई लस डट एफएन गरेर लियो के लस निकाल्यो, लस इज इक्वल टु लस निकाल्यो. अप्टिमाइजर इज जेरो ग्रेड गरेपछि लस ट्रेनलाई ब्याकवर्ड गरिदिने, त्यसपछि अप्टिमाइजरलाई स्टेप गरिदिने. Simple, it's simple. It hasn't changed practically at all, except that we don't pass params explicitly to model since the model itself holds its parameters internally. There is one last bit that we can leverage from torch.nn, the loss. Indeed, nn comes with several common loss functions. Among them are nn.msc, mean square error, okay, which is exactly what we defined earlier as our loss function. Loss function in nn are still subclass of nn.module, so we will create an instance and call it as a function. In our case, we get rid of the handwritten loss function and replace it with, okay, linear is equal to गरेर त फङ्सन मात्र गरेँ अप्टिमाइजर छ ट्रेनिङ लुप भयो यो पास गरेछ अरू केही गरेछ र everything else out input into our training loop says the same. Even our result remains the same as before. Of course, getting the same result is expected, as the difference will imply a bug in one of the two elements. Finally, our neural network. It's been a long journey. There have been a lot of explore for those 20 something lines of code we required to define and train a model. Hopefully, by now the magic involved in the training has vanished and the left room for the mechanics. What we learn so far will allow us to own the code we write instead of merely poking at a black box when things get more complicated. There is one last step left to take, replacing our linear model with a neural network as our approximating function. We said earlier that using a neural network will not result in higher quality models since the process underlying our calibration problem was in fundamentally linear. However, it's a good to make the leap from linear to neutral neural networks in a controlled environment so we won't feel lost later. Replacing the linear model, we are going to keep everything else fixed, including the loss function, and only redefine model. Let's build the simplest possible neural networks, a linear model followed by activation function feeding into another linear model. The first linear and the activation layer is commonly referred to a hidden layer for the historical reasons, since its outputs are not observed directly but fed into the input layers. While the input and the output of model of the size 1, they have one input and one output features. The size of the output of the first linear model is usually larger than one, recalling our linear explanation of the role of activations. This can lead different units to response to different range of the input, which increases the capacity of our model. The last linear layer will take the output of activations and combine them linearly to produce output values. There is no standard way to depict neural networks. Figure 6.8 shows two ways that seems to be somehow prototypical. The left side shows how our network might be depicted in basic introductions, whereas a style similar to that on the right is often used in the more advanced literature and research papers. It is common to make diagram blocks that roughly correspond to the neural networks module PyTorch offers. Through sometimes things like the 10H activation layer are not explicitly shown. Note that one somewhat subtitle difference between the two is that the graph on the left has the input and the intermediate results in the circles as the main elements. On the right hand, the computational steps are more prominent. इनपुटबाट लिनियरमा गयो 13 डाइमेन्सनमा, त्यसरी 10s लगायो, लिनियर 1 लगायो किनभने आउटपुट त 1 नै चाहियो, त्यही भएर 1 मा लगायो लास्टमा गएर. ओके, सिक्वेन्सियल मोडल इज एनएन्डर सिक्वेन्सियल भित्र एनएन्डर लिनियर एउटा 1,13 एउटा इनपुटबाट 13 आउटपुट फिचर्समा लगायो, 13 आउटपुट फिचर्स त्यस पछाडि 10h लगाएँ, त्यसपछि nn डट लिनियरतिरबाट 1। त्यसपछि के गरेँ, सिक्वेन्सियल मोडल मतलब लेखेर चाहिँ आउटपुट गर्दाखेरि त्यो आयो भन्ने कुरो। Okay, the end result is a model that takes an input expected by the first model. Module specified as an argument of an dot sequential passes intermediate outputs to subsequent modules and produces the output written by the last module. The model fans out from one input features to 13 hidden features, passes them through a 10h activation, and linearly combine the resulting 13 numbers into one output features. Inspecting the parameters, calling models.parameters will collect weight and basis from both the first and second linear models. It's interesting to inspect the parameters in the case by printing their shapes. Param shapes for param in sequence parameter. Vectors dot size. These are the these are the things that our optimizer will get. Again, after we call model.backward, all parameters are populated in their grad, and the optimizer when updates their values accordingly during the optimizer step. Call not that different from our previous linear model. After all, they are both differentiable models that can be trained using gradient descent. As few nodes and parameters of n modules. When inspecting parameters of a model made up of several submodels, it is handy to be able to identify parameters by name. There is a method for that called name.parameters. Name.parameters त ऊ भइसक्यो त, अलग अलग डिप्लिकेटेड फर्ममा छ त होइन र भने नेम प्यारामिटर्स आई थिङ्क युज नगर भने जस्तो लाग्थ्यो त नेम प्यारामिटर्स parameters तर I found name the parameters will lose the key and parameters in my model, but model that cannot how to fix this. Okay. Named parameters control F. Named tensor. Okay, name tensor चाहिँ बरु हराउन लाग्यो भने ठिक हैन आई थिंक. So it is a prototype मात्र हो तर नेम टेन्सरमा अब रहेछ तर नेम प्यारामिटर्स त हामीले सरी त्यो के हुन्छ. So for name param in sequential model, okay, print गर्दाखेरि out 0 weight bias. The name of each model in sequential is just the ordinal with which the model appears in the arguments. Interestingly, sequentials also accept an ordered list in which they can name each model passed to the sequential. Okay, from collection import ordered dictionary. Okay, sequential model ordered dictionary. Okay, hidden layer non nn dot linear गरेर पास गरेको hidden activation nn dot. Okay. Nice. So order dictionary भनेर पास गर्दाखेरि यसमा की भ्यालु गर्दै पठाएको हो र हिडन की यो यताको भ्यालु की भ्यालु गरेर पास गर्न मिल्दो रहेछ. This allows us to get more explanatory names for submodule. So for name parameters in sequence model, name parameters गर्दाखेरि आयो. This is more descriptive, but it does not give us more flexibility in the flow of data through the networks, which remains a purely sequential pass-through. The NN sequential is very aptly named. We'll see how to make full control of the processing of the input data by supplying an module ourselves in chapter 8. 7 next. We can also access a particular parameters by using submodules as attributes. Sequential model dot output linear bias गर्दा नि parameter containing दिँदो रहेछ. Okay. This is useful for inspecting parameters of their gradients. For instance, to monitor gradients during training, as we did at the beginning of this chapter. Say we want to print out the gradients of the weight of the linear portion of the real layer, we can run the training loop for the new neural network model and then look at the resulting gradients after the last approach. Training loop pass comparing to the linear model. We can also evaluate the models on all the data and see what is different from a line format. Okay, this is not a line, this is a cancer, a little bit of curve. Okay, from matlab input pyplot hplt value t range is toss dot range 20 देखि 90 अनि स्केच 1 गरे ओके ओके केही पनि गरेन एक्स्ट्रा एक्समा लेभल वाइलाई लेभल गर्यो प्लट ओके प्लटमा टिवाई नम्पाई टिवाईलाई नम्पाई टिवाई र टिसी नम्पाईलाई ओ भनेर पास गरिदियो ओके plt डट प्लट टी रेन्ज नम्पाई ओके टी रेन्ज नम्पाई सिक्वेन्सियल मोडल ओके सिक्वेन्सियल मोडल भनेर सी भनेर पास गरिदियो plt डट प्लट टी डट टियु नम्पाईलाई सिक्वेन्सियल मोडलमा फेरि पास गऱ्यो ओके डिट्याच गरेर डिट्याच गर्ने भनेको त सिपियुमा ल्याएको आई थिङ्क सिपियु डिट्याचले त सिपियुमा आउँछ होइन र नम्पाई यो फङ्सन चाहिँ म याद गरिराख्नु पऱ्यो यसलाई म युज गर्छु पछि We have covered a lot of in chapter 5 and 6. Although we have been dealing with a very simple problems, we discovered building differentiable models and training them using rendition. You first using raw autograd and then relying on NN. By now you should have confidence in your understanding of what's going on behind the scene. एक्ज्याक्टली यही बुक पढेर चाहिँ सबै इन्फर्मेसन चाहिँ पाएन तर बाहिर पढेर चाहिँ सकेँ भन्नु पर्यो Hopefully this test of PyTorch have given you appetite for more. No exercise. Summary. Neural networks can be automatically adapted to specialize themselves on the problem at hand. Neural network allows easy access to the analytical derivatives of the loss with respect to any parameters in the model, which makes evolving the parameters very efficient. Thanks to it, automated differentiation engine AutoGrad, PyTorch provides such derivative effortlessly. Activation function around linear transformation make neural network capable of approximating highly non-linear functions at the same time keeping them simple enough to optimize. The NN module together with the tensor standard library provide all the building blocks for creating neural networks. To recognize overfitting, it is essential to maintain the training set of data points separate from the validation set. तर योमा चाहिँ यसको कुरै आएको थिएन अघिल्लोमा पो आएको थियो आई थिङ्क च्याप्टर 5मा पो कुरा थियो त ओभरफिटिङ त यसमा छँदैछ त्यही पनि लाग्छ देयर इज नो रेसिपी टु कम्पेयर ओभरफिटिङ but getting more data or more variability in the data and restoring the simpler models are good start. Anyone doing data science should be plotting data all the time. That's great. त्यो त मलाई थाहा थियो परे सो च्याप्टर 7 नेक्स्ट टाइमलाई हो I think कति पेजको छ 64 वर्ड 92 92 लगभग 28 के छ यसमा डाउनलोडिङ त्यसो चाहिँ बनाउने हो डाउनलोड गर्यो डाटा सेट ट्रान्सफर्मेसन डाटा लोडिङहरु कुनमा छ यसमा डाटा लोडिङहरु सिकाएन क्या डाटा सेट त रहेछ के अरे डाटा लोडर पनि हुनुपर्ने हो डाटा लोडरहरु चाहिँ maybe यसमा सिकाएन र नेक्स्ट टाइम हेर्नुपर्ला च्याप्टर 7 28 पेज जति रहेछ 26 28 28 पेज च्याप्टर 7 नेक्स्ट टाइम